Section 4.10, the rationalization of structures. There are two general rules. Rule 1, larger ions tend to have a larger coordination number. This is simply to maximize the electrostatic attraction between this large ion and its surrounding counter ions. Rule 2, smaller ions tend to have a smaller coordination number. Well, this is because this smaller ion is surrounded by counter ions. If the center ion is small, then the electrostatic repulsion between the surrounding counter ions is big. To minimize the repulsion, we need a smaller coordination number. Now, for example, lithium plus and copper plus, they have smaller ionic radii, therefore their coordination numbers is usually small, between 4 and 6. Cesium plus is pretty big in size. It has a large ionic radius, and therefore cesium plus tends to be surrounded by many counter ions, between 6 and 12 counter ions. So when you have 12 counter ions, you have 12 attraction terms between this cesium plus and its surrounding 12 counter ions. So again, over here, we try to maximize the attraction between opposite ions. Over here, we try to minimize the electrostatic repulsion between the counter ions that surround this lithium plus or copper plus. The ratio between the ionic radii of the cations and anions also determine the structural type of the ionic compound. So what you need to do is first to compute the ratio. You always put the smaller ionic radius on top and the larger ionic radius on the bottom. And then you get a ratio of 1 or less than 1. If the ratio is 1, then you will have a coordination number of 12 for both the cation and the anion. If a ratio is between 0.7 and 1, more likely you will see the coordination numbers of 8 and 8 for cesium chloride or 8 and 4 for calcium fluoride. What's the difference? Over here you have a 1-to-1 ratio between the number of cations and the number of anions. Over here the ratio is 1-to-2. So in this case, for calcium, you have a coordination number of 8. Each calcium is surrounded by 8 fluorine, and then each fluorine is surrounded by only 4 calcium. If the ratio is between 0.4 and 0.7, and then we'll have the coordination numbers of 6 and 6 for sodium chloride in this case. Again, there's a 1-to-1 ratio here. Each sodium is surrounded by 6 chloride. Each chloride is surrounded by 6 sodium plus. However, if the ratio between the numbers of cation and anions is 1-to-2, then the coordination number for the cation here is 6. The coordination number for this oxide is 3. So again, this ratio is equal to this ratio. There's a 1-to-2 ratio here, and therefore there's also a 1-to-2 ratio here. Because again, each titanium is surrounded by 6 oxide. Each oxide is surrounded by only 3 titanium 2+. What if the ratio is between 0.2 and 0.4, and then the coordination numbers are just 4 and 4 for the cation and for the anion as well? For example, in zinc sulfide. In this case, you have zinc 2+, which is really, really small. You have sulfide 2-, which is really big. And again, in this case, well, you have a coordination number of 4 for the zinc 2+, and the same coordination number 4 for sulfide. And why does the ratio determine the structural type? So, simply put, when you have the ratio between the ionic radii of the two ions, it will determine the interstitial space between the larger ions. Again, if you have a really large ion paired with really small ion versus the ions with similar sizes, that will give you different volume for the interstitial spaces between the larger ions. So overall, these coordination numbers help the ionic structure to minimize the electrostatic repulsion and maximize the electrostatic attraction.